Where we left off last time. So I think we were talking about this circuit last time, trying to solve it, and we were trying to find the currents labeled in the circuit. So how did we go about this? Can somebody sort of give me a scenario? How do we go about finding the different currents in the circuit?
First, the ones on the right.
First, what? What's the process of finding the current, all the currents in the circuit?
You have to find the equivalent resistance for the full circuit.
Exactly. So we will combine R4, R3, and R2 together, so we can find some equivalent resistance, and then
That's in series with the time.
that's in series with this, so we can add them up, add this equivalent parallel resistance of all three to this R1 in series, and then take this 20 volts divided by this new number that we got, and then hence we will get this current I1. If we get this current I1, then we also have the voltage across this resistance. So we can use, for example, this loop here. If we use this loop here, we go around the loop starting from this node. We know that minus 20 volts, and then plus this volt, because the current is flowing into the positive node of the resistor. So when we define the current in this direction, if it was a positive number, then we can put a plus terminal here and a minus terminal here across the resistor. So minus 20 volts plus the voltage across this resistor, which is equal to I1 times 10, which we found from our previous analysis. And then there's a plus sign here and a minus sign here because of the direction of the current. So minus 20 volts plus this voltage plus the voltage across this resistance is equal to 0. And then we know the voltage across R1, we know the 20 volts from the 20 volt supply, so we will be able to find the voltage across R2. If we find the voltage across R2, this same voltage is across R3, also across R4. So we take this voltage divided by the value of these other resistances, and we will find the current in each of these branches, right? That's one way to do this. Yeah. There's another way to help speed this up. So it's the same, the logic is the same and the proof will be the same, but sort of we will introduce some rules that will help you do this a bit quicker in this class. So if, for example, we knew what I1 current was, right? We will come up with a rule called the current divider rule. So if using this current divider rule, instead of going through the logic of doing Kirchhoff voltage law here and then find the voltage and divide it by each of the resistances, we will come up with a rule based on the same analysis that will tell us, okay, if you know this current here and you know these three resistors, how would you find these branch currents? We will prove that quickly and do some examples. So we will not be doing something new really. Everything we will do today is really based on Kirchhoff voltage law, or Kirchhoff voltage law around the loop, or Kirchhoff current law at a node. Everything we will do is based on that. But we will sort of come up with interesting ways of representing, or come up with different interesting rules or laws that will help. Okay, by just looking at the circuit and knowing certain values, you can easily find the rest by just memorizing some or using some certain equation that you will have in your equation sheet. Okay, that's the objective of today's class. So, and that we will call voltage and current. This is what we will call the voltage and current divider rules or circuits. Yeah. Okay. So, for example, you have this circuit here, where you have a resistance, 3 resistors connected across a supply, right? The current I flowing in the circuit can be found from what? By taking this voltage V total and dividing it by R1 plus R2 plus R3, right? That's the current that's flowing in the circuit. If I know the current flowing in the circuit, I can automatically put the polarities across the resistors, right? So current goes into the positive terminal of the resistor. So if current is flowing this way, right, then I can put the polarities of the voltages across the 3 resistors in this fashion. And I will label them V1, V2, and V3. So if I would like to know what V1 is, I will take this current and multiply it by this resistance R1. If I want to find V2, I will take the same current, right, because it is a series circuit, multiplied by the resistance R2. If I would like to find V3, I will take the same current multiplied by the resistance R3. And that's what we have here. But we know that this current is equal to the total voltage divided by all of the resistors in series, right? So this current I is equal to the total voltage, V total, divided by all the resistors in series, right? That is this current. This V total divided by the sum of the resistances is I, correct? So what do you notice about the equations, the way that the equations are written up here? Yeah, we know that the voltage across any of these elements is a proportion of the total voltage, right? So this proportion depends on the value of the resistances in the circuits. So if we look at what the three equations give us, we see that if we want to find the voltage across resistor 2, it is equal to what? The total voltage multiplied by some ratio. This ratio is equal to what? This ratio depends on the value of this resistance, obviously, and the value of the other resistors. We know that it depends on that. But what did Kirchhoff voltage law and Kirchhoff's and Ohm's law make this dependency or this ratio look like? This is what we have here. So we derive this. We know that these are correct. But what this tells us is if I want to find the voltage across resistor 2 or V2, I can just take V2 is equal to V total multiplied by R2 resistor divided by the total resistance in the circuit. Similar thing with V3. If I want to find V3 or the voltage across resistor 3, it's equal to V total multiplied by R3 divided by the sum of the three resistors in series. Right? This is nothing new, right? This is just from Ohm's law and the relationship between voltage and current that we derived. But it has a certain shape. And this shape allows you to sort of come up with a rule called the voltage divider rule in this case. Right? Whether you want to use it or not, it's up to you. It will help you simplify matters. It will help you to speed things up. Right? So if you're given this, instead of going and saying, okay, if I want to find the voltage across resistor 3, what will I do? I know the value of the resistors, and I know the current. So, and I know the voltage source. I would, for example, find V1, which is the current that I know, multiplied by R1. Find V2, which is the current that I know, multiplied by R2. And I know my source voltage, so what I would do is take my source voltage and subtract these other two from it, and whatever's left is going to be this V3, right? So you can go about it that way. Or you can say, okay, these are three resistors in series, total voltage is divided amongst these voltages in a certain proportion. The voltage divider rule tells me that that the proportion across resistor R3 is equal to the total voltage multiplied by resistor R3 divided by the sum of the three resistors, right? So it's something that will help speed things up for you, right? It's no new information, just speed things up for you, right? And this is what we were just saying. It's of the total voltage, the fraction that appears across a given resistor in series is the ratio of the given resistance to the total resistances that are in series. So let's look at how we apply that here. So here we have a circuit, three resistors in series. What we want to do is find the voltages V1 and V4, right? Without spending too much time on analysis and calculating all the drops and subtracting from each other, we can automatically go and say that voltage across V1 is equal to what? Voltage V1 is equal to the total voltage multiplied by the resistance R1 divided by the sum of the four resistances that we have, right? You can do that. Or there's nothing wrong with, okay, I have 15 volts as a source. Add all of these resistors as R equivalent. Divide 15 volts by R equivalent. Find the current. Find the current, then multiply by this value of resistance, then that is V1. But V4 will be a little more complex. It will take more time because you have to find this voltage drop, find this voltage drop, find this voltage drop, and knowing the source, do Kirchhoff voltage law around the loop, this will be the only missing value, right? It takes more time. Versus if you do the voltage divider rule, What is V4? V4 is equal to 15 volts multiplied by 6 kilo ohms divided by the sum of the 4 resistors, right? It's a lot faster. And here they have the solutions for you. So it's here 15 volts multiplied by 1 kilo ohm for R1 divided by the sum of the resistors. And the other one is the other corresponding resistors. So everybody's okay with this, the voltage divider rule? Just a nice way to simplify your solutions. So if you don't have time on the exam, it's because you use the other way, right? If you finish early, that means you use the right, the quicker way of doing things. Okay, same thing with the current, right? So if we have two resistors in parallel, in this case, and we know the total current coming into this parallel combination, we know that current will go into each of these branches, right? Current will flow into this branch, it will also flow in this branch. And it will flow into the branch depending on the value of its resistance versus the resistance of the other branch, right? If the other branch has lower impedance to the current flow, more current will flow in the other branch, right? So it highly depends on the resistance of the other branch, right? So what the current divider rule tells us is, if I would like to know the current in branch 1, which is I1, I take the total current multiplied by the resistance in the other branch, because it highly depends, I just said, it highly depends on the resistance of the other branch, right? And then divided by the total resistance, right? So I1 will equal I total multiplied by I R2 divided by R1 plus R2, right? Because again, current flowing in one of the branches will highly depend on the impedance of the other branch to current flow. If the other branch has a very low impedance to current flow, it will consume a lot of the current. A lot of the current will flow in the other branch. So you have to, it's dependent on the other branch's impedance to current flow, right? So do you have to do it that way? No, you don't have to do it this way, right? What you can do is, here, these two resistors are in parallel, right? Find R equivalent. If you find R equivalent, then this current I total is flowing into the R equivalent. And since they're in parallel, then they will have the same voltage across them. So if you find the current flowing, the total current flowing in both of them is this I total. The R equivalent is some value equal to R1 times R2 over R1 plus R2. That's the parallel combination of two resistors. So if you take I total multiplied by this R equivalent, you will find the voltage across R1 and R2, the equivalent resistance. If you have the voltage, then you take it and divide it by the resistance, you will find the current in this branch. Take it and divide it by R2, and you will find the current in the I2 branch. Right? So you can do it that way, slower. Won't finish the exam. Okay? So it's just a way to simplify math. Right? So everybody's okay with this? Let's do some more examples. We'd like to find the voltage Vx. Vx is the voltage here across the parallel resistances, and the current, source current and I3, source current IS and R3. Okay, so what do we do? Can somebody walk me through it? I have voltage source here. What's the voltage value? This is 100 volts, 60, 30, 60. This is 100 volts, and then this is resistance here, this here, 60, 30, 60. I don't know if it's ohms or kilo ohms, but let's just put ohms for now. Okay, and I want the source current, IS, and I want this current, I think they call it R3, and we want, I think, Vx, right? Which was the voltage across this parallel component, right? So how would we go about it? Always start from the end, away from the source, okay? Okay, so I have these two resistors in parallel, so I can find the equivalent. R equivalent for these two is equal to what? This multiplied by this divided by the total. Okay, this multiplied by this divided by total. Okay, so it's 30 times 60 divided by 90. What is that? 18 divided by 9, right? Right? Yeah, 180 or 18. 180 divided by 90 is like the same as 18 divided by 9, right? Is it? Yes, I only cancel one. Sorry, 180 divided by 90. So, yes, I didn't take my multiplication table seriously. 1800 divided by 90. Sorry. That's 20 ohms. And it's even recorded, man. You can blackmail me now. So, I won't post this video. I'm just kidding. So, but I will erase it so that there's no reference to my poor multiplication skills. And I can go and edit the video and delete that section. So this is 30 times 60 divided by 90, which is 1800 divided by 90, which is 20. I'm not going to go through the pain of editing the video, so you will have... Anyway, so we have R equivalent, right? So this is this voltage source here, this resistor here, and this resistor here. This is 20 ohms, and then this is 60 ohms. This is 100 volts. So I can find my source current this way. I source is equal to what? I source is equal to 100 volts divided by 80, and I won't attempt to do the math. So it's 10 over 8, 5 over 4, what else? 1 and 1/4. So anyway, so it's 5 over 4 amps, right? That's the source current that we have in here. So if I have my source current, that means I have this current here, right? This is equal to 5 over 4 amps. I can keep this is my current 5 over 4, right? I can just keep it as 5 over 4, multiplied by 20, and then I would find Vx that way, right? And then I can take Vx and divide it by 30, and it will be this current. And then Vx divided by 60, and it will be my I3 current. I can go that route. Or, since I only need I3, right, I can do what? I can take my Is, which is 5 over 4, right, and then do what? For I3 is equal to, it's a ratio of Is. So it's Is multiplied by the ratio of Is that depends on the impedance of the other branch to sucking the current out of the source, right? So it's Is multiplied by 30 divided by 30 plus 6. Okay? Let's see. Okay. So we found the equivalent impedance, or resistance, and then after we find the equivalent resistance, they use the voltage divider rule to find the voltage. So they did a better job than we did, right? Because what did we do? We found the equivalent resistance, and then we found the source current. But we needed to find the source current anyway. So we found the source current, and then we took the source current, multiplied it by this equivalent resistance to find the Vx value. We can also find Vx by what? Initially, right at the beginning, we could have found Vx by what? Voltage divider rule, because if I have my, after finding the equivalent resistance, you can find the equivalent resistance, and instead of taking the voltage, dividing it by the total resistances to find the current, and then multiplying it by the one of the resistance values, you know that Vx, after finding this equivalent resistance, Vx will be equal to what? A proportion of the total voltage multiplied by the equivalent resistance divided by the total resistance. Here we didn't save too much time because it's a simple network, right? But you could have found Vx in a different way, right? Using voltage divider rule. After you found Vx, which is a proportion of Vs from B, so they did the same. Yeah, after that, you have to do the same thing. To find the current, the source current, you have to take your total voltage, 100 volts, or what they did was they took Vx and divided it by, so they took the voltage across this equivalent resistance, divided by this resistance, and then this is the same series current, right? Again, here you don't save too much time, but in a more complex problem, you will save a lot of time by applying current voltage divider rule and current divider rule, right? So here they use the voltage divider rule to find the voltage across the equivalent resistance, take this voltage divided by the resistance value to find the current. This current is for a series circuit, so this is equal to the source current. But then you have to go and then you can use current divider rule. Then did they use current divider rule after that? Yeah, then they use current divider rule here, right? So to find the current I3, right, they use current divider rule. So current I3 is equal to the total supply current multiplied by a ratio. This ratio depends on the other impedance in parallel, right, over the total resistance. And they found the value for that. Or they did it in the other way as well. You can take Vx and divide it by 60 ohm. Right? So many ways to skin the cat. Okay, current divider rule. You want to find the current I1 in this circuit. So we have 15 currents coming into this node, right? How do I go about this? I want to find the current in this branch. We took the current divider rule. The current divider rule says that the current in this branch is equal to the total current multiplied by a ratio. This ratio depends on the resistance of the other path that the current can take. The other path that the current can take has two other resistors in parallel. So we first find the equivalent resistance of this 30 ohm and 60 ohm, which is this 20 ohm, and I won't attempt to do the math again, right? So 20 ohm here. This 20 ohm now is in parallel with this 10 ohm, which is where we want to find the current. So current divider rule says I1 is now equal to 15 amps multiplied by 20 ohms divided by 20 plus 10, right? Okay. 15 amps multiplied by 20 ohms over 20 plus 10. Okay, so this sort of helped us speed things up, right? Now we get into more complex circuits. We will find other things to speed things up for us in these circuits, besides current divider rule and voltage divider rule. But they're all based on the same thing, really. If you don't want to do any of this, and you just do loop analysis, you will get the same result. But if you have multiple loops, how do you deal with it, right? This is what we will sort of address, because we just here what we've been talking about is mainly simple loops that we've addressed, and these loops would have maybe one unknown. But if you have multiple loops with multiple unknowns, right? What we addressed so far is we had a situation with multiple loops, but we only had one unknown. But now we will look at circuits with multiple unknowns in the system. So to do that, we come up with other tools. So one tool will be nodal voltage analysis. So what does this tool do or mean? It's a technique in which we use Kirchhoff current law, so nothing new. You will only use Kirchhoff current law and Ohm's law and Kirchhoff voltage law. really that's all we will be using. And we will use that to look at current at a node and relate the current at the node to the different voltages around the circuit. So what does that mean in English? What does it mean in English? So let's say I would like to find the current through R4. How would you do that? You're given the values of all the resistors. So let's say you're given the value of all the resistors and you're given the voltage source. And I want to find the current through resistor R4. How would you do it with the current, with what you currently know? Let me draw it up separately. I have a source here. I have a resistor here, resistor here, resistor here, resistor here, I guess, a resistor here, right? Yeah. What do I do? This is the source, this is R1, R4, R3, R2, R5, whatever it is. So, well, how would you go about this? I want to find the current through this branch. Very tough, right? It's not simple like, okay, go away from the source, find what's better and what's in series, and then figure it out, right? Because this is in parallel with what? With many things. That's what we'll end up doing, right? So we will have to figure out a way to, one way you can do it is you do a loop here, put a loop, work around the loop here, and work around the loop here. If you do that, what will you get? You will get, and you can do another one here as well. So all of these 4 loops will give you different equations that contain the value of voltage drops across all of these values of resistors, right? And if your number of equations and number of unknowns are equal, then it's a linear system and you should be able to solve it. That's one way to do it. And we will do it that way in a little bit. So we will build up to that. Another way to do it, for simple circuits, this is still simple, right? For simple circuits, what if you're able to find the voltage here? This at this node, I call this V2 node. And this is my, plus minus, so this would be my 0 volts, this is my 5 volts, for example. So this is my reference, 0. This is my 0 volts. So everything is measured with respect to 0, right? Your battery has a positive terminal with respect to a negative terminal. A negative terminal will be our reference in our circuit, right? So now this is my reference. This is why my negative terminal of the battery is connected, right? This is where the negative terminal of the battery is connected. So this would be my reference. So this is V2 with respect to 0. So if I know V2, if I take V2 now and divide it by R4, because on one side I have V2 of this resistor, on the other side I have 0. And what did we remember when we were talking about current polarity and notations and stuff like that? We were saying that current goes into the positive node of a resistor and exits the negative node of the resistor, and the current will look this way. And if this node is called V2 and this node is called 0, then the current flowing here is what? Is we call it IV2 0, right? We call it IV2. This node we call V2 and this node we call 0, so it's IV2 0. This IV2 0 is equal to what? It's equal to V2, or the voltage at this node, minus the voltage at this node, because we assume that the polarity is this way, right? So, like here, if this is A, B, right? This is 5 volts, right? VAB, which is the positive polarity, minus the negative polarity, right, is equal to 5 volts. What does this translate to? This is the voltage on one side of the battery minus the voltage on the other side of the battery, or with respect to the voltage on the other side of the battery. Right? So, and this applies to any node, not just this battery. This battery is an element. Like any element, I have the voltage on this side minus the voltage on this side divided by the resistance of this element will give me the current. Or the voltage on this side and the voltage on this side is equal to the voltage difference across this element. Right? So I have the voltage across an element, right? And this element happens to be a resistor. Then I take this voltage divided by the resistor, and I will get the current flowing through it. Right? So if I'm able to find V2 somehow, then I should be able to find this current without too many problems. So let's see how we can do that. How would you suggest doing that? So I know this 5 volts. I know that this is a 5 volts, for example, right? So what is the voltage here with respect to my reference? So this is 5 here, right? This is 5 volts, right? And this is 0. How about this? V2 is equal to what? Equal to 5 only? If V2 is equal to 5, then they're parallel. They're not parallel. There's something between them. Exactly. So this resistor, let's assume the current flows in this direction in this resistor. So current flows from the positive terminal of the resistance to the negative terminal. So this is VR1 across the resistor. So V2 will be equal to what? It's equal to 5 volts. So 5 volts. So I go, it's 5 volts. Is this the same polarity or opposite polarity? So I'm going around the loop this way. This is minus plus, and then this is plus minus. It's opposite polarity, right? So 5 volts minus VR1 is what V2 is equal to. But what is VR1? VR1 depends on the value of current flowing through this resistor. So this tells us that I need to go and do Kirchhoff current law around at this node. If I go do Kirchhoff current law at this node, I know that everything coming in has to equal everything coming out, right? So let's go back to a meter going. So let's say, so we'll assume current comes into this node from the source, and then current comes out of this node to this resistor, and then current comes out of this node into this resistor as well. And we'll call this, for example, B3. Okay? So let's go back to the drawing that they have, because I messed this up a little bit, and see and look at an example. So if I do that, sorry, the example will help. If I do that, if I do what I was just saying, I found the relationship between V1 and V2, right? With what I did. With what I did here, if I do Kirchhoff current law at this node, I know that current coming out of the battery, let's assume I know that, for example, is equal to this current plus this current. What is this current equal to? This current in R1 is equal to what? Is equal to, remember, the current through the resistor is equal to the voltage across it divided by the resistor. Right, this is a resistor, right? This is a resistor. If you want to find the current through a resistance, I, you will have to know the voltage across it and the value of the resistance, right? V equals IR, right? So I don't know I, that's what I want to find. Assuming I know R, then the only thing left is the voltage V across the resistor. The voltage across an element is equal to the voltage on one node minus the voltage at the other node. So the voltage at the positive node that I've assumed positive minus the voltage that I've assumed at the negative node. So here I assumed what? 5 volts, and here I called it V2. V2. Okay? Which I know is equal to 5 minus VR1. That's fine. But let's call it V2. So I found the relationship between what? I found the equation that includes V2 now. Also, what else did I find? the current flowing in this branch is equal to what? It's equal to, it's a current flowing in this resistor is equal to, if I assume the current is flowing this way, I put a positive sign here, a negative sign here. How do I find the current flowing through this resistor? Same. It's the voltage across the resistor divided by the value of the resistor. Right? So what's the voltage across this resistor? 5 volts. I assume this is the positive side. Okay? I assume currents flowing in this direction. This is an assumption. Right? So it's 5 volts on one side and V3 on the other side. Right? Everybody's okay with that? So now I have, because I did Kirchhoff current law at this node, I have an equation in terms of V2 and V3. Let's say I do Kirchhoff current law at another node. Then I find another equation. Is this also going to be in terms of V2 or V3 or not? Think of it. I do Kirchhoff current law at this node. I assume current is coming in into this node, and maybe coming into this node, and maybe out of this node. For example, right? This equation will be in terms of what? The current flowing through here is the same. It's V2, it's 5 volts minus V3 over this resistance. How about the current flowing in this branch? If I assume this is the direction, then the positive is here, negative here. Then it's what? V2 minus V3 over R2. So the equation now includes V2 and V3. How about here? Sorry. How about here? If I assume the current is flowing in this direction, then it's what? This is the positive, this is the negative. It's V3 minus 0 divided by this value of resistance. So I was able to find an equation, another equation. So I found another equation, another set of equations with unknowns of V2 and V3. Right? So now I have so many equations in terms of V2 and V3, and I have 2 unknowns. I have more equations than I need in this case. Right? So you will be able to solve in this case for the 2 unknowns. That's the moral of the story. This is before we structure them in such a way that we put them in a matrix. Right? This is where this is leading. Right? I will find a way. So I have a set of equations that I want to solve for a certain number of variables. So how do I do it for a large circuit? Right? For simple circuits, we can do this node analysis, find 2 equations and 2 unknowns, and solve. Right? Larger, it will be nice to be able to put it in matrix form. And here, I have a matrix, just invert. V equals IR. And I will just invert to find, if I have missing V, I will find, given I and R, I will find V. If I'm missing I, given V and R, I will find I. So on and so forth. You just have a matrix of V equals IR. Right? Let's see how that looks in reality. We put some words around what I just talked about. So the voltages at these various nodes will be called nodal voltages, just from a terminology perspective. We also have we need to make sure we have a reference node. Our reference node will always be the negative terminal of our supply. Okay? That will always be our reference node, or ground, if you want to call it that way. That reference node is typically selected such that it's connected to many branches. So does it really need to be the negative of the supply? It doesn't, right? Any node and any voltage in the circuit is measured with respect to a reference. So you can choose your reference to be V1. That's fine. So in that case, if you choose your reference to be V1, then you're measuring V2 with respect to V1, right? And V1 happens to be 5 volts with respect to this 0 volts here, right? So that's why it's easier to assume that the reference is the 0 volts in the circuit, so that you have an absolute value for the nodal voltage, right? Otherwise, you will have voltage difference, right? You will have V2 is equal to V1 plus the voltage drop across the resistor, versus V2 is equal to 3 volts with respect to what? With respect to 0 as a reference, right? So that's why we typically take the negative terminal of the battery, or the zero, or the ground, as the reference in the circuit here. And what we will do with nodal voltage analysis, as I said, is we will be performing Kirchhoff's current law around a circuit to find a set of equations, linear equations, which we will eventually put in matrix form. AX equals B, or V equals IR. V equals IR in this case, right? So we will figure out how to do that and look at some examples. The only thing we will use is Kirchhoff current law, as we just did quickly, and we will use now doing an example like that. So this is similar circuit to what we have. The first thing we do is decide where our reference is. So our reference will be this node here, which is the negative terminal of the battery that we have in the circuit. Okay, and then I'm given 1 amp, I'm given 10 volt, I'm given the value of all the resistances. Okay, what do we want? Use node voltage analysis to find the voltages V1 and V2. V1 is the voltage here. Is there any way to find this voltage quickly by doing the series parallel combination stuff that we were doing? Not really. Right? The only way to do it is come up with a set of equations. You either put loops around these, put several loops around the circuit and come up with a set of linear equations for voltages, or you perform Kirchhoff's current law or nodal analysis, right? That's what we call nodal analysis. So one way to do it is to apply nodal analysis. So let's apply Kirchhoff current law at node 1 here. Right? So if we apply Kirchhoff current law at node 1, what do I have coming into the node? I have 1 amp coming into the node, and then I will assume that current into this branch is coming out of the node, and current into this 5 ohm is also coming out of the node. Okay? If I assume that direction, then what is this current equal to? What is the current in the 2 ohm equal to? V1 minus this node's voltage. This node's voltage happens to be 10 in this case. So it's V1 minus 10 volts divided by this 2 ohm is equal to the current coming out of this V1 node going into this 2 ohm resistor. How about here? The current, I assume, is also coming out of this node into the 5 ohm resistor. So what is the value of that current? V1 minus V2 divided by the 5 ohm resistor. Right? So this is, the one is V1 minus V2 divided by the 5 ohm resistor. The other is V1 minus 10 volts divided by the 2 ohm resistor. And that's what we have here. This is V1 minus 10 divided by 2 ohm resistor. V1 minus V2 divided by 5 ohm resistor is equal to 1. Simplify this and rewrite it, you will get common denominator, etc. You will get this equation. This equation is in terms of V1 and V2. So I have 2 unknowns. So I need another equation to be able to solve for the 2 unknowns. So the other equation I can get from applying Kirchhoff current law at node 2. So where is node 2? Node 2 is here, right? So this is node 2 that I have here. So I will apply Kirchhoff current law at the node. So how do I go about that? This current was coming in to this node from this 5 ohm resistor. So this current is equal to what? Still, it's V1 minus V2 divided by the 5 ohm resistor. Or, let's say, because they're not related, right? If I say that applying Kirchhoff current law at node 2, V2 minus V1, so they did this. They assume that the current is coming into the node here. So again, you're performing Kirchhoff current law at the node. You will assume the direction of current coming in or out of the node, right? So they assumed now in this case that all the currents are actually coming into the node. So that the V2 minus V1, so V2 voltage here minus V1 divided by the 5 ohm resistor plus V2 divided by 5. Where is 5? V2 divided, so it's V2 is minus the source or the reference divided by this resistor. The current is coming out of the node here, right? And then the last one is V2 minus 10. Current's coming out of this V2 node, so V2 minus 10 volts divided by the 10 ohm resistor, right? So we did Kirchhoff current law at this other node. So all of these currents we assumed are coming out of the node, right? So everything coming out is equal to everything coming in. Everything coming in is 0 in this case, right? Does it matter if I bring these with a negative sign on one side and bring the 0 on one side? No, it does not matter. That's why we can assume currents are coming in or out anytime we apply Kirchhoff current law at a node, right? So we apply Kirchhoff current law at this node, rewrote the equation down. We now have another equation in terms of V1 and V2. I have another two sets of equations in terms of V1 and V2. We can solve those. We can put them in matrix form to simplify the solution, right? So we can put them in matrix form. These are our two equations. We can put them into the form of AX equals B. So we write them down into matrix form, and then we have our only unknowns are now V1 and V2, right? So I can find V2 by inverting the matrix and multiplying, pre-multiplying by this vector here, right? So if I want to solve for V1 and V2, I will pre-multiply by the A inverse. This is my A. Pre-multiply by A inverse on the left, pre-multiply by A inverse on the right. So it's A inverse multiplied by B. B is this vector, 60 and 10 I have here. So X equals A inverse times B. So I will find V1 and V2 quantities. Or you can just solve them simply using the... So we'll stop here. I think there are just some more examples we will be doing next. So we'll stop here. Any questions?